Hello, this is video number 56, and I'm going to talk about torque. This is a big topic, so I know it's going to take several videos. I usually start this topic with a demonstration, and it's kind of fun, so unfortunately I can't do it right now. But what I do is I find a door in the classroom, and I go on the outside of the classroom, and I have a volunteer on the inside of the classroom, and both of us push on the door. So say this is the door right here, and this is the classroom over here. So I'm on the outside over here, and I tell my volunteer that there's going to be a trick to this that none of the class knows about. But I tell the class, I say, hey, we're both going to push on this door. I'm going to try to close the door this way. He's going to try to open the door this way. We're actually starting with the door at a 45-degree angle. So I'm actually over here and he's over here. And I asked the class, who do you think is stronger? Am I going to be able to shut the door, or is he going to be able to open it all the way? So, it's a show of strength. But the trick is, well, actually, let me not tell you the trick. And let me just tell you that I always win. So why do you think I win when I push on the door? I'm always able to close it, and the person is not able to keep it open. And then I do get locked out of the classroom, but that's a different story. So see if you can think why I always win. So it's not because I cheat, all right? But let's see if you can figure out. So this idea introduces the topic of torque, which has to do with rotation, but it has to do with the fact that a force is causing a rotation. So it turns out that there are three factors that affect the ability of a force to cause rotation. So usually the volunteer that I pick definitely looks and is stronger than I am. So the amount of force that can be applied definitely affects how much the object is going to rotate. You know that if you apply more force, there's going to be more rotation. So that is definitely one factor. Now, when we are pushing, we're both naturally pushing straight on. We don't push like this to open a door, or we don't push like this. We know from experience that we're going to push straight on. But it turns out that the angle definitely makes a difference as well. But the reason why I always win this little contest is a third reason here. So let me pull it up. So it's number one here, the position of the application of the force. That makes a big difference on how easy it is to rotate something. So you know from experience that when you're trying to open a door, you don't push very close to the hinge. That's hard to push when you push there. When you're trying to open a door, you push toward the end. So you're trying to maximize that distance from that pivot point where the hinge is to where you're applying the force. So that's the trick in the demonstration, is I tell the student, hey, you're going to push at the center of the door. I'm going to be on the outside of the classroom where nobody can see me, and I'm going to push on the edge. That gives me more leverage and more torque, and that's why I actually win. So the three factors that affect torque is where you apply the force, how strong the force is, and then the angle at which the force is applied. So I want to spend a little bit more time discussing that third condition, which is the angle. So when the force is parallel to the position vector, just think it's this R here, but just think it's your object that you're rotating. When the force is parallel, no rotation occurs. Right? If you pull on the door this way, it's never going to rotate this way or this way. A parallel force does not cause any rotation. So if you push on a door at some angle, well, a diagonal force has a horizontal component and a vertical component. And we just said this horizontal component, because it's parallel to your object, does not cause any rotation. So that means it's only the perpendicular component that causes the rotation. If you are given this angle theta that touches the horizontal, then that perpendicular component is f sine theta. But I just prefer to write it as f perpendicular, because you never know which angle that you're going to be given. So when our force is diagonal, we must find the component of that force that is perpendicular to the object being rotated, because that's the only part of the force that causes the rotation. So now we can look at the definition of torque, the first definition, and then we'll do one example using this definition. So torque is a tendency of a force to rotate an object about some axis. Torque, which we use the Greek letter tau, so don't write a t, it's a tau, equals F perpendicular R. So F perpendicular is the component of the force perpendicular to the object, and R, as you can see in the picture, is a distance from the pivot point, which is also called the axis of rotation, to the point of application of the force. The force is applied right here, so that distance R. So you multiply R times F perpendicular to get the torque. Now we do have the units for torque, which are Newton times meters because it's a force times a distance. And then the sign convention, just like for our velocity, if we're rotating counterclockwise, it's positive. For rotating clockwise, it's negative. So let me do one example using this definition. Ryan is trying to open a stuck door. He pushes it at a point 0.75 meters from the hinges. That's our distance R, it's given here, with a force F of 240 newtons, directed 20 degrees away from being perpendicular to the door. So we're given this angle here. So there's a pivot point, the hinges. You always need to know where your pivot point is when you find torque, because if your pivot point is here, well, then now your distance is much smaller, right? So always have to identify that pivot point. What torque does Ryan exert? So we're going to use our definition of torque, which is F perpendicular R. F perpendicular is drawn in this particular picture, this component right here that is perpendicular to the object being rotated. In this case, it's adjacent to our given angle, so it's going to be F cosine theta for that component. So that's why I prefer to write F perpendicular, because you never know if you have to use cosine. And then R. And now we can plug our numbers in. It's going to be 240 times cosine of 20 degrees times 0.75. Plug all of those in, and we're going to get 169 Newton times meters. And we have to pay attention to the sign. We're rotating counterclockwise. That's a positive torque. So that's the end of this video. I'll talk more about torque in the next video.